All right, folks, let's go ahead and get started. So, as far as this today's go, we're gonna talk a little bit about some sampling concepts. Optimally speaking, what I would like to be doing is I would like to be doing this side by side in unison with IDEA. I think I mentioned at the beginning of the semester. Up until this year, we've had a computer assisted auditing tool that we did projects with in this course side by side. It was additional homework assignments, which I know you're probably thinking additional homework assignment. That sucks, Dr. Barnes, but it was actually kind of cool because you actually got to do some data analytics and got exposure to the data analytics package. The reason we're not doing it now is that we ran into a problem last fall where some students were not able to access the tool and could not actually get it uploaded to their system. So basically, it was a significant amount. It was like a half of the students couldn't actually use IDEA. So basically, I've kind of jettisoned that. I'm going to probably be redesigning it in the future, but that was kind of the reason why we don't do it now. That being said, I do think there's one compelling reason for using a computer-assisted auditing tool, and that has to do with assisting in test work, particularly selecting testing samples. So I think what we're going to do, and I'm going to try to do, is we're going to walk through chapter 8 and 9 today. Then I'm going to try to jump over to show you some of the things that we could do in IDEA. These would normally be things you'd be doing for a big homework assignment. It's like a 2-hour-long homework assignment, which you would receive additional points for. Unfortunately, we can't do it. I know, darn, you're just kind of like, oh, darn, 2 more hours of homework. You know, I heard some people talking about how they're not getting enough sleep already. So, I guess it's probably good that I'm giving you that extra free time. But we are going to miss out on the opportunity to learn some of this stuff. But I think it's very interesting and relevant. And now I'm really upset because I heard a ding and I turned the sound off on this thing, and maybe that's somebody else's computer. All right. If you want to work along, I would recommend going to Brightspace in week 7. There's a file called the attribute sampling tables. I used to print these out and hand them out, but the simple truth is we're only going to be using these for a couple of things. So you may want to just have them electronically, and we'll work together through these. Depending on whether or not IDEA continues to work with me. It's working with me right now. I had to go to the virtual desktop to open it. It would not open natively on this computer, which was an example of the problems we've been running into. But if assuming it continues working, then we'll work through some problems. Otherwise, we'll address that problem when we come to it. But let's talk a little bit about sampling in the context of how it relates to auditing. Again, sampling is a fairly common concept. You've talked about it probably in your statistics classes, depending on how many you've taken. I'm going to go ahead and throw the disclaimer out there. A few things. First of all, I am not a statistics expert. If after this class you come to me and start asking me a lot of statistical nonsense and start saying, well, can you tell me about why we would use the random forest model versus another model? And I bet like words, over my head. Yeah. I will point you over the statistics direction. I have a good relationship with Dr. Alberts and Dr. Kim, and I'm sure they can actually help you, but I would not, I know enough statistics to get a PhD in accounting. That was basically all I needed to know. Also, part of the reason that we talk about this, some of this is obsolete because a lot of accounting firms, when they do statistical sampling or do sampling, they use non-statistical techniques, which are based in the theory of statistical sampling. But usually you're just kind of established and say, we're going to use this method all the time, and we're never going to use any variance in it. So they define what the parameters are, the size and the risk, and then they just use that. The only reason that we talk about this is still something that's prevalent and tested on the CPA exam. And so we need to go over it in a little bit of detail. So I do want to talk a little bit about how it relates to what we've already discussed with respect to controls. I also want to talk a little bit about the concepts of classical variable sampling, which is not something that we're going to do directly, but you'll see me do a little bit of as we move forward. So let's go ahead and get started and talk about why do auditors use sampling. Now, again, there's these concepts up here versus called reasonable assurance versus absolute assurance. Which one do we use as auditors? Reasonable assurance. Yes, we use reasonable assurance. And the reason why is because we cannot accomplish absolute assurance. That will require testing way too much information. Now, interestingly enough, you may question that. You may say, well, Dr. Barnes, I've been reading some AI articles, and they said that we could actually test entire populations now with the AI tools we have available. And I'd say, touche, you must have been sitting in my graduate class earlier today because we were talking about this. But for the most part, we still rely on sample testing. In fact, we can't test everything. Imagine trying to test all of the purchases at Amazon in a given year. That would literally take, if you're talking about one person trying to do that, that would literally take like several centuries to do something like that for a single year. It's just not practical. So the idea being is that we are going to incorporate sampling techniques based on statistical methodology, which leads to something called sampling risk, which we can kind of correlate to the risk of incorrect acceptance. So remember we talked about audit risk, and we said audit risk is the risk that we would express a clean opinion on financial statements that are materially misstated. That is effectively the correlation we're talking about here, is this idea of risk of incorrect acceptance, is that we would say something is fine when there's a problem. Now, there's also the risk of incorrect rejection, which is also a possibility in sampling, but we're less concerned about that as auditors. So generally speaking, we're talking about the idea of the possibility that a sample drawn is not representative of the population. So the auditor may reach an incorrect conclusion about the account balance or class transactions based on the sample. So we like to make sure the sample is representative of the population. That will not always 100% be the case. Usually we try to make sure that our samples are representative to a significant degree, whether 95 or 99% conclusion rate. That's kind of the general litmus that we use. So what are some concerns we talk about in sampling? These are some things that should throw back to statistics. We generally assume a normal distribution, which that normal distribution is represented by the U-shaped curve, that the median falls here, and that about 66% or 68% will fall within one standard deviation, 95% within two standard deviations. We want to make sure the samples are unbiased and random, that we have no clear distinction in selecting them. This will not always be practical. One thing that we will note when we're starting to talk about testing is a lot of audit firms, they specify that they do not use random sampling, but they use something called haphazard sampling. All right. And the difference being is that random sampling is truly at every single account or transaction in a certain area has an equal chance of being selected, or every single account has an equal chance of being selected. Haphazard basically says we're going to start with a certain threshold or a certain criteria, and then we'll select based on that criteria. So maybe we say all material accounts, all accounts over $5,000, then we would sample from those. So we would not necessarily select the small items, which has its own drawbacks. But for the most part, we would like to assume that our sampling is going to be unbiased and random. And the samples are truly representative of the population, which is, again, kind of a long assumption. But for the most part, we can accommodate that to a greater degree. We also want to make sure the variance in the sample is also representative of the population. So the standard deviations we see in the population are kind of consistent with the standard deviations we see in the sample as well. Now, that is all pretty much a review of what you probably talked about in Stats 220. If you've taken any other statistics classes or statistical testing classes, you're probably fairly familiar with these concepts. Let's talk about how they truly relate to audit testing and what it is that we're concerned about. So first of all, we need to understand when we're going to use attribute sampling versus variable sampling and what the difference between those two concepts are. Attribute sampling is basically testing for a specific characteristic. Does a specific characteristic exist within the items that we're testing? Variable sampling, on the other hand, extrapolates dollar value differences in a sample to the population. So this is going to be monetary unit sampling, calculable variable sampling techniques, things like that. The big difference between that is just when we would use these particular items. Tested controls often use attribute sampling, which makes sense because when we're testing controls, we're effectively trying to say, does the control work, yes or no? So the characteristic we're testing for is the control effective? So attribute sampling is our primary usage for testing controls. And maybe not exclusive, but I would say 99 times out of 100 are going to use attribute sampling for testing controls. And then test of account balances, which are going to be our substantive testing, those are going to be that we often use variable sampling. So this is where we actually look and see what is the deviation within the sample that we've tested, and then how does that deviation reflect on the population as a whole? So say we sample 1/100th of the population. Roughly speaking, any differences we see in the sample would be expanded 100 times that. Now, that's not a perfect assessment. It's going to be something around 100 times, but you kind of get the idea, is that a amount that we see, a difference we see in the sample is going to be projected to the population as a whole. Now, some concepts that we need to be aware of. So let's talk about some things we need to know before we can actually move on with our sampling approaches. So first of all, confidence level. Confidence level is our confidence the sample was tested as representative of the population. Larger confidence levels will require larger samples. I want you to make a note of this because this is something that often comes up whenever you see this concept used. You're going to see the term confidence level. You'll also see the term sampling risk, and these are related concepts. In fact, confidence level is basically 100% minus sampling risk. So 100% minus sampling risk equals confidence level. So if I tell you my sampling risk is 5, what does that tell you about confidence level? 95%. Yes. Okay. If I tell you my sampling risk is 1%, that's going to tell you confidence level is 99%. Good. Okay. Simple math. But yeah, and the reverse is also true. If I wanted to actually reverse it and say, what is my sampling risk based on my confidence level? If I have a confidence level 95%, sampling risk is 5%. So they do have a relationship there that basically they sum together to equal 100%, so we can determine either one from those. Next, we have some related concepts called tolerable deviation rate and expected population deviation rate. These are really confusing if you're not familiar with statistics and at least familiar with statistics. So I want to kind of explain these at a basic level, and then we'll see some examples of these, how these work together. So the tolerable deviation rate, it sure sounds like tolerable misstatement, and it's very similar to that concept, except keep in mind that we're not testing monetary dollar amounts, we're testing characteristics and attribute sampling. So tolerable deviation rate sounds like it basically is the deviation rate in the sample the auditor is willing to accept. So we may say like the deviation rate, we would accept a deviation rate of 8% in the sample. Like 8% of our items could be inconsistent with our expectation. Then we have the expected population deviation rate, the deviation rate that the auditor expects in the population based on history. Or they also call this a historical defect rate. So we would assume that we look at the sample and the way it's performed, or we look at the population and the way it was performed over time, and we would expect deviations to be around 3%. Now, there's some interesting things that are pointed out here. So first of all, the tolerable deviation rate always needs to be greater than the expected population deviation rate. Always needs to be greater. If they're the equal or if the expected population deviation rate is greater, then we've got a problem. And think about it intuitively, okay? Say that you can tolerate 5%, but you expect the population to have 10% failure rate. Can you tolerate what can you tolerate what the given failure rate is in the population? You can't tolerate that. Your expectation is higher than what you could tolerate. So basically, you would have to test everything in the population because you're not sure what a representative rate would be. So we always want our tolerable deviation rate to be bigger than our expected population deviation rate. In fact, this relationship dictates sample size. So as confidence level increases, we increase our sample size. As the distance between these two numbers increase, so the distance between, so as tolerable rate gets bigger, our expected population deviation rate gets smaller, then our sample size gets smaller. So the bigger the distance is, the smaller the sample size is. If I make that sample size or that difference smaller, as these two numbers come closer to one another, our sample size increases. So there's an inverse relationship between the distance between these two numbers and our sample size. Now, something you probably remember, but it's still worth talking about. Unless the population is relatively small, which is less than 1,000 observations, population size is not highly correlated to sample size. So everybody remember that from statistics and say, that doesn't make any sense to me. How can I have a population of 10,000 and then another population of 1 million and they could use equal sample sizes? And I'm just going to say, that's statistics. That's just the way it works. So population is generally not highly correlated. Is it correlated? Yes. Okay. Highly correlated. Not really. Once we get past 1,000 items, there's usually a very minimal effect. Okay, doesn't matter how big we make the population; it just doesn't change that much. All right, so let's go ahead and put these concepts into action. All right, this is a problem 827 in the book, which you're going to do something like this in homework. So remember those tables that I said that you pull up on Brightspace. What I'd like to do is I'd like to go ahead and walk through these based on these tables. All right, and if you got access to the tables, great. If not, look over somebody's shoulder. If you don't have access, or you can just kind of patiently look up at me and assume that I knew what I'm talking about. But I'll try to show some of this as we work through it. All right, so I'm going to show the tables for the first one, and then we'll try to work through the rest of them together. So as we see here in this table, we've got 4 different control procedures, and we're trying to determine, we're eventually going to determine whether the control is effective based on these information. But the first thing we have to do is establish sample size. So we've got a risk of incorrect acceptance, which is our sampling risk, which is 5%. Tolerable deviation rate of 6%, and expected population deviation of 2%. So you notice tolerable deviation rate is 6%, this is 2%, so the tolerable deviation rate is bigger than our expected population deviation rate, which is good. We can't tolerate those being too close to one another. Also, if sampling risk, this number right here is 5%, what does that mean about confidence level? 95%, okay, 95%, which is important. So here's what we're going to do. We're going to go to this first set of tables that are on Brightspace. And I'm just going to zoom in. So you'll notice up here, this says 95% desired confidence level at the top, which is where we want to be, okay? There's also some for 99% or 99% confidence level, which will be relevant here in a second. But remember we said our tolerable deviation rate is 6%. Our expected population deviation rate is 2%. We will notice here that our sample size needs to be 127. Does everybody see how that came up? Just the alignment in the table? Now, there's a couple of items to note here. Okay, 127 is what we want our sample size to be. That's what the statistical analysis tells us. You will notice there's a number in parentheses next to it says 3. And you're probably asking, what does that number mean? This is attribute sampling, and it's basically telling us that we can tolerate up to 3 failures in our tests before we can conclude the sample or the control is not effective. So we start testing, we're going to test 127 items, and if more than 3 of these do not meet the characteristic we're testing for, then we can conclude the control is not effective. If less than 3 or 3 or fewer are basically fail the test, then we can conclude the control is effective. But we'll see that here in just a second. We'll see how that works. Okay. So let's go ahead and do the rest of these based on these tables. All right. So we said this is 127 right here. All right. Actually, I just realized why it tells you how behind the times I am things. I've actually got I got this set up. I got this already set up. My gosh, guys, it's amazing you all haven't fired me already. All right, 127. All right, oops, I was already in there too. All I have to do is go like this. So like when your past self does something and you suddenly realize your past self did something really cool and it makes your job easier. Yeah, now I'm patting past Michael on the back. Good job. All right, so let's go ahead and go look. So 95% confidence level again because of risk acceptance. Tolerable deviation is 7%, 2%. So we can go ahead and go to our table again. So we'll do this one together. 7%, 2% says 88. I believe that's what I correct. So 88. Yeah. So we're going to go and put 88 in there. Now we've got 10%. So if it's 10%, we've got 90% confidence level, which means that we have to scroll down to our next table, which is 90% desired confidence level. And I believe it's 4% and 1%. So 4% and 1%, so 96. Is everybody with me on that one? And then I'm just going to plug this in so I don't have to look. If I do 10%, which is 90% confidence level, and 3% and 0%, I'm going to come up with 76. I believe it's what I have. Yeah, and I keep trying to type it in when it's already in there. All right. So this is telling us what our sample sizes are, and I'm going to go ahead and drag this down because we're going to do our testing in the next area, but I already have these plugged in down here. All right, so the next thing we need to talk about, we've established our sample sizes, but what else do we need to do? Well, next thing we need to do is we need to determine what is our sample deviation rate. So we're going to test these controls by testing every single one of the instances of these controls, every single transaction. So we pull out 127 transactions and say, I'm going to test if this transaction met the particular control parameters. So everybody remember the test of controls we did back in chapter 6 from last week? And you say, all documents have to be stamp paid, all right? That was a control, and we tested that control as part of our chapter 6 testing. So imagine we did that 127 times. We looked at 127 voucher packages, and we checked and see, did every document get stamp paid in the voucher package, all right? If the answer is yes, then we say the control worked in this situation. If the answer is no, we say there's a deviation. There's an example of where the control failed. So we're going to determine after we test all of our sample, how many in the sample failed. And it's a simple calculation. It's the number of deviations divided by the sample size. Then we got to do something called the upper deviation rate, okay? So the upper deviation rate is a little bit fuzzy. Think about it this way. Basically, we've got a sample size, and we say a sample percentage. So let's say we do our testing, and we assume that 3% of our sample, or we did our testing, or say 3% of our sample failed. So we have to calculate the deviations that 3% of the sample did not pass our testing. Does that mean the population is also 3% failure rate? We don't know, okay? We don't know what the population deviation rate is. It's likely, let's see, do I have a pen that I can use here? So I'm going to put this up here. So it's likely that if it's 3%, that what happens to the population is somewhere in the range of, say, maybe 1% to 5%. And I'm making these numbers up arbitrarily. And you guys now see why I don't write on the board very often, because my handwriting is horrible, okay? Especially when I'm trying to do something off the spur of the minute. So it's probably within this range of 3% to 5 or 1% to 5%. We as auditors aren't concerned about what the bottom limit is, because we're never going to consider the bottom limit. We are very concerned about the upper limit. So we're going to try to extrapolate, what do we think the upper population deviation rate is? What is the highest possible deviation rate we can see in the population based on a 3% deviation rate? And that's this upper deviation rate that's calculated here. And basically what that is the sample deviation rate plus something called an allowance for sampling risk. Now, this allowance for sampling risk is something that will be given to you. It's given in the problem, but it will actually be the sampling deviation rate plus some arbitrary, not arbitrary, but statistical allowance that's stapled on. What do we do with that? Once we've calculated our upper deviation rate, we say that if the upper deviation rate is less than the tolerable deviation rate, we include the test support the conclusion the control is operating effectively. In other words, let's say that I calculate an upper deviation rate of, well, what did we say in that first scenario? An upper deviation rate, we'll say 5%, okay? I don't know what the actual number is, but at 5%. My tolerable deviation rate is 6%. So what I can tolerate is 6% failures. I observe that the population, the highest likely error estimate for the population is 5% errors. So if the population is likely to fail 5% of the time, but I can tolerate up to 6%, what is my conclusion there? Am I okay with that? Yeah, I'm good with that. Now, let's go ahead and consider the alternative. What if the upper deviation rate is greater than the tolerable deviation rate? We conclude the tests do not support the conclusion the control is operating effectively. So now I actually calculate my upper deviation rate. My upper deviation rate is 10%. My tolerable deviation rate is 6%. So the highest possible amount that the population could be is 10% failure rate, but I can only tolerate up to 6%. So the population deviation rate, upper population deviation is 10%, which is greater than what I can tolerate of 6%. I say the control is not effective, is not operating effectively in that scenario. All right, let's go ahead and look at some examples of this now. So this is going to use the second series of tables in that document that's on Brightspace. It's also in the book. Okay, so let's just go ahead and do some calculations. So in this particular control procedure, you will notice that it gives us a certain number of deviations. All right, a certain number of deviations. Now we're going to calculate the sample deviation rate. All that has to do is we're going to take 4 divided by 127. So 4 divided by 127 is 3.1%. I can do this for all of the others as well. 2 divided by 88, 2 divided by 96, 0 divided by 76. And that's where I come up with sample deviation rate. This 0 was particularly interesting because basically we had no control failures in this one at all. Now we need to compute the upper deviation rate, which, remember, we said that if it's 3%, if it's roughly around 3%, that our true population deviation rate is in some range, okay? We want to know what is the possible upper error limit, the upper limit of that range, all right? So that's what the calculation is. This is, we're going to use that table again. So we're going to go back. Oops, wrong table. Look at this table here, and we're at 95% desired confidence level. So we have found 4 deviations in a population of 127, which we don't have 127 on the table, we just have 125. But you'll notice it says 7.2. So it's telling us that the possible highest error or highest limit on the population deviation rate, the highest range could be 7.2%. All right. So 7.2% is the basically upper limit, and this should be percentage, by the way. I don't know why I didn't put percentage on here, but assume it's a percentage. I'm going to compare this to my tolerable deviation rate that's given up here. This is what I can tolerate. This is what I project the highest level the population could be. Do I accept this control as effective? What do you think? Nope. This number is larger than this number, so I conclude the control is not effective. All right. Let's do this. Let's do this one more time over here. So we're going to do 88 and 2.3%. Okay, sorry, two deviations at 88. So sample size of 88. We're going to go back to that same table. So 2 deviations, sample size of 88. It really kind of is tricky which one we're going to use. The default would want to be 90, but the simple truth is conservatively, we would want to use the lower error number. Now, this is going to lead to a bit of a problem because we will have 6.9 here and 7.7 here. If we use 7.7, which is what I used here, we're going to say the control is not effective. you're probably making an argument, say, Dr. Barnes, that's not fair because you used the lower rate where 90 was closer than 80 was. And I say, you've got an argument, okay? But for conservative reasons, if we're using a table like that, we want to use the number that's lower so we have a higher range, a higher estimate. Because if this is 6.9, this generally comes over. The simple truth is this the actual number here, as we're going to see, is much lower than this, but we're trying to be conservative in our estimate. There's some problems with that though, because what happens is that when we do the rest of the testing, you will notice here that we've got a 3.3 computed upper deviation rate, which is greater than our 3% tolerable deviation rate. So that's saying the control is not effective. Does anybody see a problem with the conclusion on this last control right here? Me concluding the control is not effective on this particular last scenario? There were 0 deviations. How could the control ever be effective under these circumstances? So there's a problem with this imprecision of this statistical testing. Using a table is generally going to be less precise if we're doing statistical analysis, which is going to lead into my discussion of idea here in just a second, because we get a lot more precision when we use an automated tool. But that being said, this is kind of what we come up with. Now, those are some examples, and you're going to be doing some of this for your homework. When's the homework? I guess that would be Friday. So yeah, you'll be doing some of this for your homework, very similar to that, using those same tables. So you may want to keep those as reference. But the last thing I want to kind of talk about before we talk about some idea examples is how does this differ from other types of sampling? So the first scenario was controls testing. I think controls testing is very, very transparent, but we can also use sampling to actually test account balances. So think about it. We've got a balance of accounts receivable, and the accounts receivable balance for an organization is made up of thousands of customers. Do we want to test every single one of those customer accounts? Probably not, okay, probably not. So we're going to select samples of those customer accounts and test based on that balance of the customer accounts we tested, what is the actual balance within accounts receivable? And we're going to assume that any differences that we observe are going to be representative of the population. So we have a few concepts that we need to actually include in here that are a little bit different. We're still going to have confidence level. Confidence level does not change, okay? 95%, 90%, 99% in some extreme scenarios, those are going to be pretty high. But the other thing that we need to talk about is how do the other elements change? Well, the first one is we're going to be using our tolerable misstatement now. So tolerable misstatement is the maximum amount of misstatement in a specific account or disclosure the auditors will accept, which you know that. Tolerable misstatement is inversely proportional to sample size. Does everybody remember that discussion back in chapter 3 when we talked about tolerable misstatement? I say we'd like this number to be as large as possible so that our sample can be smaller. If we make tolerable misstatement really, really small, that means that we have to do more testing, which is intuitively sensible because we have to check and make sure that we're smaller and smaller errors. Our projected misstatement is similar to our expected or allowed or historical deviation rate. This is the estimated misstatement in the population or account disclosure. So, or I guess actually this projected misstatement, this is upper EV deviation rate. My apologies. So our projected misstatement is less than or greater than tolerable misstatement. We include the counter disclosure is not or is not fairly stated. So in other words, we're going to compare these two amounts. All right. If we project that the misstatement of the population is greater than what we can tolerate in an account, then we're going to say that account is not fairly stated. On the other hand, if we do the projected misstatement and we say the projected misstatement is less than the tolerable misstatement, we can say that's less than materiality, less than the tolerable misstatement account. We're fine with that. Now, I'm not going to go too much into detail in the calculations for this. Is it possible to do this using handwritten techniques? The answer is yes. We could do tables on this too. It's a lot more challenging, and frankly, I think that's a little bit beyond what we need to know. But I am going to kind of show you some basics about how we would do this using statistical tools. So your focus should be for this particular chapter is make sure you focus and understand the testing for attribute sampling, understand how the statistics for that works, and understand the basic concepts for variable sampling. The idea that we're going to extrapolate and project an amount based on the population as a whole. All right, now let's hope my idea is still up and working. So what I want to show you now is one of the things that we can actually do with a computer-assisted auditing tool that makes things life a lot easier. So I'm going to close this, come back over here. I haven't signed out, so I was so worried because whenever I open view.truman.edu, if I go to another window, usually sign me out, and I'll have to go back log in, and I was worried that I was going to have to go back. But we're still here. We're still up and running, okay? So that's a little victory for us, okay? So yeah. Everybody give a silent cheer. Excellent, excellent. Well done, well done. That was the most silent I've ever heard. All right. All right, so let's go ahead and look at what we can do with attribute sampling. So in an idea, basically, we don't even need to have a population to do some basic analysis. So if we go to analysis and go to attribute, we can do some calculations here. So let's just go ahead and do some very, very basic ones, and we're going to change our deviation. Let's say I've got a sample size of 1,000. All right. And then I'm going to say my tolerable deviation rate is 8%. My expected deviation rate is 3%, and my confidence level is 95. Okay. Which you've seen those concepts before. So I can just plug those in, and IDEA will actually come up with my information here. It says sample size 91. All right. The critical number of deviations of the sample, that's the number in the parentheses. It has to be at least 3. So it gives us that information and tells us basically all we need to know. We can calculate the sample just by putting it into a tool, which I know you're kind of like saying, I can do that with a table, Dr. Barnes. That's not impressive. You're right. That is not that impressive. Okay. But there's some interesting takeaways that we can actually have here, some things that we can actually look at that will help out. So let's go ahead and reinforce some of the things that we've talked about already. So what did we say about confidence level? Confidence level, is it directly proportional to sample size or indirectly proportional, inversely proportional? It's directly proportional. So if I make sample size larger, sample size goes up, or sorry, make my confidence level larger, sample size go up. If I make confidence level smaller, sample size go down. So let's test that. Let's change confidence level to 90. What should happen to the sample size? Should go down. And in fact, it did. If I made it 90%, it goes down to 63. Okay. So yeah. All right. I hit enter. Yeah. Okay. All right. So let's do some other stuff. What happens if I set my expected deviation rate to 4%? Okay. So I'm changing it 3% to 4%. Now we know the relationship is between these two items here, tolerable deviation rate, expected deviation rate. And we were concerned about the distance between these two items right here. Does everybody remember that discussion? So if I make this 4%, that distance is going to become smaller, and it has an inverse relationship between that distance. So if I make this distance smaller, what should happen to my sample size? Should go up. In fact, it does. It went up to 123. And it works for either one. I can actually change this over here. I could change this to 7%, and it may not be the exact same change, but it will still affect the sample size. So it's 122 if I change that one here. Here's an interesting one. Okay. Here's an interesting one. Let's speculate really quick. Let's just say that I say this tolerable deviation rate is 8%. My expected deviation rate is going to be 7.99%. What do you guys think the sample size will be on this one? I'm going to say it's going to be 1,000. Tells us we have to test the entire population because there's not a difference between what's expected and what the historical defect rate is. What about this? Okay. I'm going to set this at 10%. I'm going to set expected deviation rate above tolerable deviation rate. What's IDEA going to do? Yep. It tells us there's an error. We can't actually have where expected population deviation rate gives us a tolerable deviation rate higher. So it kind of reinforces everything we were talking about earlier. Let's do one more. There was one more that I kind of overlooked. All right. So population size. So we're at 1,000. What happens if I set this to 10,000? What do you think is going to happen to sample size? Actually, let me go ahead and set this to 1,000 so we can reestablish. So this is 91. If I set this to 10,000, what's going to happen to sample size? You think it'll go up? It'll probably go up a little bit, maybe like 1 or 2 or a few items, but not very many. Okay. It went to 95. What if I set this to 100,000? 95, 1 million, 95, 10 million, 95. Is everybody kind of seeing where I'm going with this? Once we get past a certain threshold, the population size doesn't matter. Okay. It did a little bit from 1,000 to 10,000, went up by a whole whopping 4 items, and then did not change when I kept adding zeros on there. My speculation is that I continue adding zeros here. Population size must be between, it has a range on population size. Okay. What is that? 2 trillion. It has a top end of 2 trillion. So you note your computer assisted auditing tool has a range of 2 trillion. I've never done that before. I was just curious. Yeah. All right. So yeah. So that's an easy way to identify our sample size and some interesting conclusions that we take away. Now let's go ahead and let's do some testing now. Let's evaluate samples. All right. So here's what we're going to do. Is we're going to assume that I've got a sample of 52 voucher packages. Remember those voucher packages we did testing back in chapter 6? Okay. We're assuming that I'm doing testing of those, but I've got 3 different controls tests that I do a part of those voucher packages. Okay. So remember when we did those voucher package testing, we had 5 different controls. I'm going to simplify this. I'm going to make this 3 different controls, but the same 52 voucher packages. So I'm going to say population size of 1,000, because our sample size is going to be 52. And we're saying desired confidence level of 90. Now we're going to test a couple different situations that we're going to determine whether or not the sample exceeds. We're going to say tolerable rate of 7.5%. That sounds good. Tolerable deviation rate of 7.5%. Let's just go ahead and test the deviations in the sample. So let's say that I'm testing and I have 2 deviations in my first control. My first control, I test 52 items. 2 of them did not work. They did not meet the control. So I can type this into IDEA and it basically says, here's the deal. The population deviation rate we could see is probably 9%. Now that's not the sampling deviation rate. 2 divided by 52, roughly about 4%. But the true deviation rate falls between 0 and 9, or well, not 0, but close to 0. And they're saying 9.7 deviate, or 9.7. And the level of imprecision has a lot to do with the fact that this is a lower confidence level. So it's 9.7%. Now, what did I say that my tolerable deviation rate was? 7.5%. So if I've got a population deviation rate of 9.7% and I can tolerate 9.7%, or sorry, I can tolerate 7.5%, what do I conclude as an auditor? Is this control operating effectively or not? It is not, okay? This is too large. All right, now we've got a second control that we're testing, and this one has the same sample of 52, but it only had 1 deviation. So this is 7.1%. So a tolerable deviation rate is 7.5. Upper deviation rate is going to be 7.1. What do we conclude about the control? Thumbs up, thumbs down. Thumbs up, okay? Control is operating effectively, it's less than that. But just for posterity, 0. So the one-sided upper limit, it should be 0 because we found no deviation in the control, right? No, we're still going to have some number in the upper error limit. Keep in mind that even if we test the sample and found 0 errors, there's probably some errors somewhere in the population. So this is accounting for the fact that even though we were really lucky and got a sample that was perfect, we're probably not perfect in the population as a whole. So the population as a whole could have up to 4% of deviations in there. So that's the way to interpret those results. Okay, so let's just go ahead and really quickly, since we got an opportunity, let's go ahead and go back to what we talked about earlier. So I want to go back to, actually I want to go back to the sample evaluation over here. So remember here when we said that, we'll say, I'm going to put a number in here that's arbitrarily large. I'm going to say 500,000. So remember we had a sample of 88. And the number of deviations in the sample was 2. And this is at 95%. This was actually our example that we did. This one right, the second one right here. And I said it was not effective. And we made the argument saying, well, that's not fair because we used 80 as our sample size in the table. The nice thing about using a computer assisted auditing tool is I don't have to actually use it around. I don't have to round to 90 or round to 80. I can actually put to 88 and I come up with more precision. So if I do that, here's an interesting one. It says the one-sided upper limit is 6.98%. Remember our tolerable deviation rate in that example, in that one, was 7%. So as an auditor, what are you thinking right here? Auditor, you're just kind of like, wow, that was close. Yeah. Tolerable deviation is slightly greater than the population upper error deviation rate. So we can actually allow this control to be effective, which is good because if we're using the table right here, we have not effective. So I'm just going to change this. I'm going to say effective. Yeah, with the lowercase e. Yeah. What about that example that we looked at before where we said desired confidence level of 90%. We tested 76 items. And we had 0 deviations in the sample. That's 2.98, which is less than that 3% tolerable deviation rate. By the way, I do want to make a note of this, okay? If you ever go in the real world and audit testing, and you have a manager that gives you a tolerable deviation rate of 3%, you are allowed to immediately go on Glassdoor and complain about the company, okay? This is unreal. This should never, ever happen. These low tolerable deviation rates should never happen. That's just setting an auditor up for failure. If it's not 5% or higher, then yeah, you basically riot or make AI do it. One of the two, all right? So last thing I want to talk about some of the possibilities when we actually are doing some advanced testing. So I'm not going to go into a lot of detail of this, but I do want to kind of show what the tool is capable of. So remember we talked about classical sampling. So let's Let's go ahead and do a monetary unit plan. And so basically what we're going to be doing here is we're going to allow the information. Let's see, I need to have an item open. So let's go ahead and go to the accounts receivable file. There we go. I didn't want to open a file because I didn't know if it was going to work, but I'm going to do it here. Okay, so there we go. Analysis, monetary unit plan. All right. So it's going to look at these numeric value items. We're going to use invoice total. And we're going to set confidence level at 75%. Now, I want to make a note of this. Never, ever in history has an auditor legitimately used 75% of his confidence level. Think about what the implications of that are. If you go to the client and say, I'm 75% sure the financial statements are free from material misstatement, what's your client going to say? Say, well, what was the point in hiring you? You're basically saying that 1 out of every 4 transactions could possibly be a material misstatement, or 1 out of 4 items, situations would be a material misstatement. 75% is way too low. I would argue 90% in the modern day and age is probably too low. 95% is more likely, but I like it. But they did, for simplicity purposes, in the example that I'm using here, 75%, just to kind of keep this easy. Then we can input $30,000 here. Expected error of 1,000. All right, so the expected error is kind of that same parameter as the expected population deviation rate we have to input here. And then value of the sample population. It's already completed. So yeah, it should be the invoice total field. So yeah, it actually has this up here. So we don't have to do any calculation. The idea already does it for us. So it clicks on estimate. And basically what it does for us right here is it says an approximate sample size of 28 is required here at a sampling interval of $20,053.13. It's actually going to be attributable to 75%. Now, keep in mind, this is not an appropriate rate to use. More likely, we want to be at 95%. What do you think is going to happen if I set this estimate? What do you think is going to happen to our sample size? It's going to go way up. It's going to go way up. It's going to go up to 59. Okay, so it over doubled when we increase the confidence level. If I increase it to 99. Then we're getting close to the population, because the population itself is only 454 records or 454 transactions. So yeah, the sample is going to be testing it. Now, what's interesting about this, it kind of gives us some information about how we can actually set up our population for sample testing. It says that if we want to do this at 75%, which again, idea is not a human being. It's not saying that's absolutely ridiculous. Quit messing with me. It just says, okay, fine, 28 items. All right. So we want to use an interval of items, and we can actually set this up that it would select a random sample for us that we could use for testing, which is really kind of cool, because if you think about the way that we would do this naturally as human beings, is that we would try to identify random items just haphazardly, just kind of pick them out. Idea will say, I'm going to take an interval, and then every $20,000th dollar, I'm going to select that transaction for testing. In this case, we're doing accounts receivable. So at every $20,000, I select a customer that I'm going to select, and that it doesn't matter what the customer's dollar balance is. I just select the $20,000, and that's how I pick up the randomized sample. And if I pick at least 28 items, then I can test at the 75% confidence level. So let me ask you real just quick conceptually. I'm not going to go through the entire exercise because we're not focusing on confident or classical variable sampling. But let's say that I'm an audit associate that's doing this testing right here, and I don't know much about sampling, and I'm like, well, 28 doesn't seem that much different from 20. So what if I just do a nice round 20 sample? Okay. If I test 20 items, is that going to be sufficient for this particular test right here? Will I achieve 75% confidence? No, I will not. Okay. I have to actually meet the parameters here, which is why when we say something like 95%, it jumps us up to 59 items. It's so consistent that we have to, or so important that we actually test all of those items within that range. And the higher that confidence level gets, the more required items that we have to test. So this is an important conclusion, because we're trying to get a greater level of precision in our expectation. Keep in mind that if I'm saying 75% right down here, I'm testing 28 items, and then I can go to the client and I can say, all right, we did our test work. After our testing, we are 75% certain that your financial statements are or are not materially misstated. Again, if you went to a client and said 75%, what would their response be? To get out. All right, get out. So the reason this whole point about 95% being so important is that it requires a lot more work here. And this kind of tells you specifically, I shouldn't say kind of, it tells you specifically what the work level would be for this particular type of transaction. So again, I'm really sad. I know that you guys are probably happy not to have to do the extra work, but this is kind of an interesting tool that you can utilize for techniques like this. I do think that there's probably going to be more of this available in the future in different formats, but I just wanted to give you a little bit of insight of how we can actually use these tools, these technology tools, to make our jobs a little bit easier. All right, you don't have to be a statistics expert, as I have obviously shown. All right, homework on Friday. I'll see you all then.
So, quick question.